So he will be talking about overcontact binaries, tell us more about that. Please, Matthias.
Thank you. Thank you. Good afternoon, everyone. Also, everyone following online. In the next sort of 30, 40 minutes, I'd like to walk you through the work I've been doing in the past year and also planning to do in the next couple of years or year, which is an effort in advancing our modeling of overcontact stars, more specifically massive overcontact stars. And in this talk, I will go over how to do this actually in 1D stellar evolution codes, more specifically in MESA. So the context about this is that there's a huge observational backing that, of course, lots of massive stars are in binaries. In the massive star end at the O star level, so above about 10, 15 solar masses, about 70% of all stars strongly interact with a companion. So binarity is not certainly not a niche component of massive star evolution. Now, in the same way, contact configurations of massive stars is also not a niche phase, as at least around 30% of them experience a contact phase at some point in their lives. 24%, at least in this pie chart, comes from the merging binary stars, as an overcontact system is a necessary precondition of a merging binary. And in the same way, during heavy mass accretion, either by envelope stripping or accretion, there is also a brief contact phase as matter is dumped on the secondary, and it piles up in a sense. Binarity, of course, has an important implication for stellar evolution of binaries, and in particular, this advent of gravitational wave astronomy and observed binary black hole coalescence, understanding the evolution of massive stars and binary interaction will help us understand the observed population of such black hole mergers. Going back to stellar mergers, these are these weird kind of objects that can produce all kinds of exotica in stars. For example, here on the right, you see a figure from Fabian Schneider's work in 2019, where he simulates in full 3D magnetohydrodynamics how a merger can actually induce high magnetic fields in binaries. So on the top, you see the density profile, and in the bottom, during the merger, you see that mainly non-magnetized material after this merger creates a very high magnetic field, up to 10 to the 7 Gauss in this example. Now, not only that, there are these again weird exotic objects called long gamma ray bursters and superluminous supernovae. And merged stars can create conditions for these phenomena to occur. In the world of overcontacts, there are the low mass siblings, which are called the W-UMA systems, after their canonical W Ursa Majoris star. And they experience sometimes what we call red novae. Here we have on the right a light curve of V1309 SCO, or called nova SCO now, where the magnitude of this object increases by multiple orders of magnitude. And a study in 2011 from Tilena et al. Show that this is perfectly consistent with a merger of two solar type systems. And in fact, if you resolve the range just before the merger into its seasons, then you can see that the slide curve is oscillatory. And in fact, the period of this oscillation decreases exponentially, which indicates a dynamically unstable situation. And this is indeed the case when, for example, mass is lost through the outer Lagrangian points, or if the system is Darwin unstable, the period of this binary shrinks exponentially until the merger, which then corresponds to the red novae that was created in 2008. Now further on these, let's say, unstable contact binaries, it was long thought that actually overcontacts with a mass ratio away from unity are in fact impossible. It was shown by Kuiper in 1941 that it is simply impossible due to the mass-radius relation of stars and the mass-radius relation of the size of the Roche lobe, that two stars with different masses cannot be normal stars in a contact configuration. So this led to believe that, okay, all of these contact systems in principle should be quickly dynamically unstable and either merge or detach or disperse, whatever. Still, we observe a lot of them, as I show in the top bullet point. We observe lots of them in the Ogle catalog, for example. And similarly, on the massive end, we observe several overcontact systems. Here we have V382 Cygni with masses 19 and 26 solar masses. So mass ratio, again, appreciably away from unity. This was modeling done by our ex-PhD student, Michael Abdul-Masih. And in a massive star regime, this means that actually, statistically speaking, we should be observing long-lived contact configurations. So there are, due to the IMF, few massive stars. There are even fewer that are in contact. But if we observe them, then statistically, we should observe them in long-lived phases. One of the major results also from Michael's work is that the secondary in this contact configuration is actually way over luminous. And if we look at this in an HR diagram, we see that the secondary, which is 19 solar masses, if this were a single star, or if you would consider the core properties, let's say, then it should be at the bottom right in this figure. But actually, we observe it. These are the open colored symbols, depending on the model that he used. We observe it several times more luminous, also considerably hotter. So the question is, how can such a star be moved in the HR diagram by that amount? Several suggestions has been made. One is already up there. Is there maybe some very efficient mixing going on in this star that sort of keeps the star young and keep it hot? Or is this mutual? Oh yeah. For this internal mixing, we have the problem that observationally we would expect then lots of CNO processed material at the surface, but that's not what Michael finds. Similarly, for mutual irradiation, we would expect some signal in the photometry, which we don't see. So maybe it is heat or energy transfer in this contact configuration, so that the hotter companion or the more luminous companion transfers energy to the secondary, making it indeed more luminous and higher temperature than its core mass would indicate. So in the modeling of overcontact binaries, we face lots of challenges. For example, the effect of tides on the stellar structure has never before been studied. The stability of mass transfer due to these tides will be affected. As I said, energy transport in non-equal mass ratio binaries is also not being considered yet. And then there is, of course, this question of rotational mixing or other mixing processes. Could this somehow better reconcile our modeling with observations? In this talk, I will be mainly focusing on the first and the third points, namely how to do stellar tides in 1D stellar evolution and how to tackle the problem of energy transfer. Tidal deformation. So let us take a step back and consider again how we do typical 1D stellar evolution, for example in MESA, but there is of course other codes. We typically take a set of differential equations, of which I show here 3, the mass continuity equation, the hydrostatic equilibrium equation, or pressure gradient, as well as the temperature gradient, or the equation of radiative transport, which is, of course, applicable in radiative envelopes of massive stars. When you write these equations down, you assume that this star is indeed made out of spherical shells, so tiny shells in the center, stacked on top of one another. When you go out, that means, of course, no rotation can happen in these shells, because otherwise the symmetry is broken, because they bulge out near the equator. And similarly, no binary companion can be close by, because it would tug on these shells, and again break the nice 1D spherical symmetry that we need for the left-hand side equations to apply. So when we now go to a Roche potential, where we have two stars with masses M1 and M2, by the way, in the massive star end at least, we expect lots of mass to be condensed inside the core. They're very centrally condensed. And so we can approximate these with point masses at these locations with a certain separation, of course. Drawing then the equatorial plane of the Roche potential gives you a picture like that, with the 3 collinear Lagrangian points shown, as well as some extremal lobes in blue. The Roche potential here on top is, I've written it in a dimensionless form, of which the first 2 terms represent the gravitational attraction of both the component stars, and the last 2 terms represent the rotational motion around the center of mass of these two these two stars, and I indicate the mass ratio Q as M2 over M1. So we want to relax our assumption in stellar structure. We want to relax the assumption of spherical symmetry, but we have to, of course, keep some of these assumptions. One of them is that rotation is no longer free. We have to fix or tidally lock our 2 stars to the orbital velocity, because in fact the Roche potential is written down in a co-moving frame with the Keplerian orbital velocity as a parameter. And lastly, we hold on to this assumption of shellularity. So instead of building up the stars with spherical shells going from the core outward, we build up the star with deformed shells. So they will look more teardrop-sized, teardrop-shaped when you go out to the Roche lobe, and they will look peanut-like in overcontact. The shellularity means that wherever the potential is constant, so on equipotential surfaces, we expect the pressure, temperature, density, and in fact all other quantities to be constant along the shell. How can we then proceed in practice? We will apply the method developed by Kippenhahn and Thomas, and later extended by Hendel and Sophia in the 70s. The philosophy of this method is to actually divide out, in a sense, the non-trivial geometry of the problem, to, in fact, return to a sort of spherical system. And in practice, we will do then, we will consider then, for example, a differential volume d phi, I've highlighted there in darker green, and consider the volume that this encloses v psi, and relate then, or create then, a new independent variable r psi, which is the simple spherical relation actually. So we create what we call an equivalent radius r psi, and use that as a grid, in a sense, to build our star upon. The bottom equation then relates, or shows you how to relate the differential volume to differential mass, so the mass contained in the shell, and as rho is assumed constant on this shell, you can write it simply like that. Similarly, with dV, you can relate that to a change in the potential space by the averaged inverse gravity along the shell, and this controls actually how thick the shell will be. Since in spherical shells the thickness is constant along a potential, but in general this is not so. about the poles of the contact system. In fact, the shells are thinner, and at the equator, the shell is slightly wider. Summarizing then all the math required for this, I have compared here the two sets of equations from the spherical side on the left to the modified non-spherical equations, let's say. And we see that the independent variable r, or m, depending if you're in a Lagrangian system, in a Lagrangian framework, these are modified to these equipotential averaged quantities m psi and r psi, and the momentum equation and transport equation are multiplied by what we call correction factors fp and ft. The fp is the pressure correction factor, and ft is the temperature correction factor. So in a sense, the fp factor in the second equation measures how the pressure gradient changes with respect to a spherical shell of the same enclosed volume. It's interesting to know that for a single rotating star potential, this fp and ft factors are known and is actually already implemented in MESA. You can look up the details in the latest MESA paper for that. So our goal here is to do this for the binary case, and I would tackle this problem completely numerically, since the potential is not as easy as a single star rotation potential and doesn't play as nice. How you go about this is you sample a certain target equipotential psi t, and you solve for the Roche surface of this by solving the equation I highlighted up there. And then you get these red points for the primary lobe and the blue points for the secondary lobe. In this example, this is Q is 0.3 with a slightly overfilling potential. When you have the surface, you can then integrate all the quantities you need to construct these FP and FT quantities, such as volume, area, surface area, average gravity, average inverse gravity, and also the moment of inertia of this lobe. Sampling then a wide range of mass ratios from 10 to the -7 to 10 to the +7, which comfortably covers all the mass ratios needed in stellar circumstances, and then going for potentials all the way out to when the primary will overfill its outer Lagrangian point. So back, where do I see my mouse? So at the back of the primary star, which is in fact hidden here, you cover all the parameter space needed to construct FP and FT. The results of this integration are concisely shown in a figure like this, where you see the pressure correction factor Fp plotted against the fractional Roche lobe size, as well as various mass ratios. So if you focus for the moment on the blue line, the solid blue line, this is the result from the integration for mass ratio equals 1, so equal masses. And you can see immediately that for smaller radius, so for shells well within the Roche lobe, in fact, the distortion is very small, and we recover that Fp is 1, and thus we are in the spherical case again. However, when you appreciably fill the Roche lobe, so close to 1, this factor drops, and at 1, at exactly Roche filling, when you have the teardrop shape, the pressure correction factor drops to about 84%, which means that the pressure gradient is reduced to 84% of what an equivalent spherical shell enclosing the same volume and mass would experience. Now, you see also that I've drawn lines, dotted lines, that signal a single equivalent. Now, what does this mean? Well, in evolution instruments, MESA for example, you can play pretend, right? You can play the game of putting stars in a binary, but consider them non-rotating or consider them rotating as single stars. And in fact, by default, if you turn on rotation and you evolve a binary, this is what's happening. So the binary module takes care of mass transfer and tracking the orbital angular momentum and so forth. But the angular momentum of the star itself and its deformation is considered as if it were a single star rotating at a given angular velocity. And the structure factors, the structure correction factors that would give are the ones indeed plotted by the dashed lines. So again, you see for very small shells, well within the Roche lobe, this is indeed the same. We approach 1 very quickly. But as you, again, appreciably fill the Roche lobe, there is some difference between the tidal deformation model, where both centrifugal and the pull of the secondary is taken into account, versus the single star model, which only takes into account centrifugal and doesn't care about the existence of the companion. So in this diagram here, I've summarized a bit how rotation, in a sense, is handled at the moment in MESA. So for single stars, when you turn on rotation, you take properties from the stellar model, such as the angular momentum, the mass enclosed, and the radius, and transform that into FP and FT from a single star description of rotational distortion. Similarly, for binaries, this is actually the same is done. The binary information encapsulated in the mass ratio Q and the separation A is just ignored, and a single star prescription is used. But what you should actually do, at least when tidal locking is assumed, is take directly the binary information in fractional separation and a mass ratio and compute FT and FP in a way that I have done in my work. Going forward from that is that the boundary conditions are actually affected as well. It is often overlooked, but the boundary conditions are in fact critical ingredients to solving any system of differential equations. The differential equations sort of govern how the bulk of the star behaves compared to whatever is on the side, but you have to explicitly give boundaries to these to close the system in a sense. And for the interior boundary condition, this is actually fairly trivial. You put R equals 0, M equals 0, L equals 0, basically any other extensive quantity to 0, and at the surface of the star, you integrate some atmospheric model as a lid. I envision this as a lid on a jar in a sense. And it is important to realize that an atmospheric boundary condition is in fact dependent on local effective gravity when you integrate through this. I have I have written here some equations where the differential optical depth d tau is actually directly proportional to g-1 times the change in potential. If you know that, if you then enforce hydrostatic equilibrium in this atmosphere, the pressure profile through the atmosphere is directly proportional to g, and you could well envision that averaged over the surface equipotential, this pressure of the atmosphere will be proportional to the average gravity, so bracket g, which is in itself proportional to these structure factors Fp and Ft, as well as the surface area S psi. For the temperature, we do the same thing, we do a similar thing. The luminosity that the surface is shooting out of the star, we want to equate this to a Stefan Boltzmann like law, where the typical spherical Stefan Boltzmann says 4 pi r squared sigma t to the 4th. Now this transforms into S psi, the modified area of our surface potential, times sigma df to the 4, and saying that this global df effective temperature is the temperature of our atmosphere, which is a choice, by the way. We come to this system of boundary conditions where I've highlighted the changes with respect to spherical to spherical boundary condition in red. Again, the pressure term modified because gravity is slightly different on the surface, and for temperature because the surface area is different with respect to spherical to the spherical law. Before showing you the results of some of the case studies I've done in my publication of just last month, I want to set a bit your expectations and say that you saw this profile of FP with R, and while you did see some differences, they are not monumental. We do not expect any monumental or serious differences from when you consider rotation in the single rotating case compared to the tidal case. However, this study or this process is in fact a critical ingredient to modeling overcontacts, or indeed tidal forces are at their extreme. With that in mind, going forward, what if we compare these implementation of boundary conditions in a simple intermediate mass rotating star? I started a simulation or a model at the ZAMS at 60% critical of a 5 solar mass B-type star, evolved it all the way to the TAMS, and at the blue hook you can see that the effective temperature is only modified by about 0.1%, so we're slightly redder, but that is certainly not anything you would be able to observe. However, when we go to the situation of a detached eclipsing binary, here I've taken your typical eclipsing binary that you would observe, a 5 solar mass star on a 3-day orbit around a 3 solar mass black hole. I evolved it from the ZAMS all the way until the star overfills its Roche lobe and goes into an X-ray binary phase. And the most important result here to see is that just before the star overfills its Roche lobe, the tidally deformed or single star rotationally deformed models give a 5% higher radius of this star. And that's doesn't seem too surprising because of course the star is being puffed up by the rotation in a sense. It is important with respect to doing precision astrophysics studies with these models. For example, an eclipsing binary, you can measure the radii to a very, very high accuracy, much better than 5% in fact. And so any study using such accurate measurements must take rotation into account, because otherwise the observational data box could, in a sense, miss the tracks that your models give. So to correctly interpret appropriate models to observe data, rotation needs to be taken into account. Secondly, the difference between these rotation models, so using either tidal forces or single star rotation, which corresponds to only taking centrifugal deformation into account, or also tidal deformation, that's of a minor difference, only about 1%. What about overcontacts? Massive overcontacts. I've evolved here two 32 solar mass stars, so a twin binary, identical components in an orbit of about 1.5 day. At LMC metallicity from the ZAMS again until they overflow their outer Lagrangian points, at which point we expect lots of angular momentum loss and a rapid merger. But this system is in fact VFTS 352 analog, which I featured on my title slide, where we have two overcontact system with a very equal mass ratio. Again, the main result of this model is that the rotating models are cooler, measurably cooler than the non-rotating track. Certainly in the contact phase, which is to the right of the dots, the models are up to 7, even 10% cooler, depending on which of the models you take. Furthermore, I'd like to highlight the top panel, which shows that in the non-rotating model, the Roche lobe size increases, which is due to mass loss when mass is lost through winds, you lose, in fact, orbital energy, which widens the orbit. However, when you include rotation and its associated angular momentum contained within the star, mass loss, in fact, spins down stars. So that means that spin-orbit coupling will, in fact, steal angular momentum from the orbit to inject it back into the stars to keep the stars synchronously rotating. And this is indeed one of the assumptions that we set out from in the beginning, that stars are continuously synchronously rotating, and indeed, certainly in overcontact configurations, we expect that tides are very efficient at doing so. In that case, the Roche lobe size decreases, in fact, and this accelerates the reaching the Roche lobe, and also accelerates reaching outer contact point, again leading in potential age differences of similarly observed stars. So again, this study did not reveal anything unexpected, but it is crucial when going forward with modeling overcontacts that we take rotation or tidal effects into account. So in the next couple months, I will be focusing most of my time to figuring out how to do energy transfer in overcontact systems, as I alluded to, which might be a very promising candidate to solving these observational clues that we have on overcontact binaries. I'd like to introduce this. I'd like to take a step back and go to the von Zeipel theorem, which is a law of radiative flux, saying that radiative flux is actually proportional to the local effective gravity. And this is in fact corroborated observationally, again by seeing that in rotating stars, for example, that the poles are in fact hotter than the equator regions, because indeed at the polar regions, local effective gravity is higher versus the equator. So we have a higher temperature, more flux, if you relate to a black body. Integrating then the flux over a surface equipotential, you can imagine that the total luminosity L psi is in fact proportional to this average G quantity that I defined earlier. Keeping then this assumption of cellularity at the surface of an overcontact binary, we say then that the surface will radiate some luminosity L1 plus L2, L1 coming from the core of the first component, L2 coming from the core of the second component. Adding to this that the cores themselves produce luminosity L1, luminosity L2, which is basically set by the mass-luminosity relation. Right? More massive stars have higher temperature cores and produce more radiation. Then it's fairly easy to see that there must be some transfer, probably right above the Roche lobe, of energy from the more luminous component to the less luminous component, in a sense equilibrating as function of the fractional areas, the luminosity from the one to the other, so that at least the higher up shells are approximately cellular. So it is indeed possible to actually prove from a purely theoretical standpoint that there must be some energy transport happening somewhere. And in fact, that's what Shu and Lubow back in the 70s did, and they constructed some very simple zeroth order approximation to this problem, where they actually compute a very simple luminosity redistribution formula, which you can see there at the top. I've taken that directly from the 79 paper, where you can see that the L1 and L2 without the primes are the core luminosities, and with the primes are modified luminosities after, at the Roche lobe contact point, after luminosity has been shifted from one to the other. when you look at this in stellar profiles, on the right I've drawn some arrows to indicate where approximately you would take these profiles. The primary, which has a more luminosity and has a steeper temperature gradient inside the Roche lobe, so for smaller r, at the Roche lobe will lose some luminosity to the secondary and therefore create a slightly shallower temperature gradient, L1 prime, or represented by L1 prime. For the secondary, who is cooler because it has less mass, you will actually have to jump up in temperature to match the temperature gradient of the primary, and that is of course by gaining luminosity in this way. Above the Roche lobe then, in fact, there's only one model, the fully cellular model of the contact envelope. So in principle, these profiles should match exactly when going through the two profiles of the two stars separately. This model has some pros and cons. Obviously, the pro is something that I said already, is that it's actually quite simple to implement this luminosity redistribution, barring of course all the technical details of mesa. But the major con of this is that instead it hides somewhat of the physics going on through the contact points and through the so the physics of actually moving this energy from one to the other is somewhat hidden in this discontinuity. And in a sense, it's slightly easier to motivate it for convective envelopes, where you can more easily imagine horizontal convection moving energy from the primary to the secondary, but that might not be too trivial for radiative envelopes. How can you move so much energy from one side to the other? So in a sense, that is hidden in this model. So I'd like to leave you with some conclusion and prospects. First, shown you that it is indeed possible to represent rotation and/or synchronized tidal deformation in 1D stellar evolution. Second, I've shown that rotation and tides affect the stellar structure in a measurable way, and that is certainly the case for precision astrophysics studies, where very accurate measurements of radii, or effective temperatures can change conclusions of such studies in a meaningful way. And lastly, I hope to have convinced you that energy transport in overcontact layers might be a very promising candidate to solving Kuiper's paradox, as well as these observational clues of seeing over luminous secondaries, as well as seeing lots of contact binaries far away from mass ratio unity. So thank you for your attention, and I will take any questions. Yes, absolutely.
So I have two actually. First one is with the overcontact spin up, spin down.
Mm-hmm.
I'm curious how sensitive you are to the mass loss rates, and which one did you use?
Yeah, so Dom asked the question about how sensitive the model of spin-orbit coupling is sensitive to the mass loss rate. So in this study, I used the Brott et al. Wins for LMC metallicity. Well, yeah, the question is definitely very good, but but indeed, I have not done any major study in changing wind prescription in that sense. But the only requirement is, of course, that the mass loss rate needs to be high enough in order for the moment of inertia to kick in and sense capture all the tidal energy from the orbit. I do not know what threshold that is. There must be some threshold where indeed this doesn't matter anymore. So where the red lines actually turn flat, right? But that is indeed something that is potentially to be studied.
Question number 2.
Mm?
With your core luminosity model, which I forget the name of now,
The
you seem very sensitive to the core size and hence its luminosity. Is that a free parameter or is that fixed?
core size is something that is indeed not directly relevant here. It's basically just the energy output that is relevant. So anything that enters the Roche limit from below, L1 for example, and L2, has to be redistributed in this average way over the surface of the whole contact system. So the size directly does not matter. But the luminosity of course does, yeah. Yeah.
Yeah, hi Matthias, thanks for the nice talk. You were talking about like this 5% difference in radius that's important for like yeah precise measurements of mass and stuff. I was wondering because the stellar structure is affected so much that during later, if you continue to evolve these kind of systems, how does that propagate in future evolutionary stages? And is there some point where you could differentiate between whether this is happening or not actually?
Mm-hmm. Yeah, so Siemens' question was, how would this 5% difference in pre-interaction or main sequence modification propagate to further evolution? Well, yeah, that's obviously the crux in the sense of the problem. I have not explored that here, but well, of course, there's an observational limit in the sense that you observe way more main sequence stars. So I focused here on the main sequence evolution. But yeah, how it would exactly propagate to later, I have no idea. I don't think it will affect whether mass transfer occurs. Mass transfer will still occur, maybe just later or earlier, depending on what model you use. But on surface properties of giant stars, I have at this point no real good answer. Yeah, but it is indeed a good study. Yeah, that some would do.
It just occurred to me.
Mm-hmm.
Do we even call this detached anymore?
Dom's question was, do we call this detached anymore? Well, yes, if you have a black hole and a star below its Roche slope, then it's a detached system. Even though it's tidally interacting, yes. And when it hits the Roche slope and loses mass to its secondary, we call this a semi-detached configuration. Are there questions from people online? Can they ask questions? Do we know? Okay, that's a pity. Yes.
This may be a little bit technical.
Mm?
I was wondering, if I, as an observer, want to use your models to match them to observations,
Mm?
then I will also be sensitive to, say, the inclination angle for observed luminosity and temperature.
Mm-hmm.
Your luminosity and temperature from your models is essentially averaged over the surface.
Mm-hmm.
How would I get a possible effect of an inclination angle?
Yes, that's so. Timothy's question was, how do observational effects from inclination affect matching observations to models? And I can answer to that by saying, okay, our models return to you, indeed these average quantities, average equivalent radius, global effective temperature, but you can always use the Roche slope geometry again to actually return back to what the local effective gravity is at any point along the surface equipotential. and then take some integration along the line of sight or along the observed face of a star to know what the temperature is that you actually observe. Same thing with radii, of course. For example, polar radii or equatorial radii are not very well defined anymore in contact systems, but using or back calculating through the Roche potential allows you to know anything you would like to know. Well, it appears so. Yeah, back in the 70s, it seems that people had a lot of time doing theory, developing equations, and so forth. I don't know what people have been doing in the 90s and 2000s, but it seems that now that we know that binarity is a key ingredient in evolution, this is coming back to the surface. We can use this in practical evolution codes. Mm-hmm.
You already mentioned a bit how to kind of break down your assumptions in one.
Mm-hmm.
But I was just like thinking, what could you change in the code?
Yeah.
How did you change? Like, is this also something you observed?
Mm-hmm. So the question from Nicolas was that, okay, what happens if we extend this to multiple star systems? I presume you mean triples at the first level. Yeah. So yeah, doing evolution for multiple star systems, detailed evolution for multiple star systems is of course a much harder problem. If we restrict ourselves to, for example, hierarchical triples, then you can model the inner binary as a binary I've prescribed right here, and then maybe model the outer star as a single star. And potentially within this triple, you can introduce some Lidov-Kozai mechanism, feedback of angular momentum, energy, pumping, eccentricity of the inner binary, etc., etc. This is actually something that I would like to explore in much later stage. But going even beyond that, to quadruples or even higher order, we can still keep this hierarchical assumption valid, because or it is a double binary with 4 stars, or it is a hierarchical quadruple, and then you would still need some assumption on I don't know, having an inner binary and then single stars further down. Because of course, doing this fully dynamically is just not possible, at least not in the framework I've highlighted here.
Maybe the second question is like, is there any systems observed where you have like contact binaries and then a triple star?
Yeah, so the question is there contact binaries observed with a triple companion? I don't know, actually don't know. There might be. It's certainly not impossible to imagine, but not that I know of. Thank you.